In this lecture, I'm going to introduce the topic of radioactivity and nuclear chemistry. So radioactivity involves changes in the nuclei of atoms. So up to this point in this course, we've really talked about changes in the electronic structure of atoms, and so we would talk about bonds forming between the sharing of electrons or ions forming by getting rid of or obtaining a new electron. But now we're going to focus on the nucleus, the protons and neutrons that make up the center of the atom. And radioactivity has a lot of problems and a lot of advantages and a lot of controversy. So we're going to talk about a few of those topics today, including diagnosing and treating medical conditions, estimating the age of fossils and rocks in the earth, energy generation, and nuclear weapons. Also want to point out that it is not nuclear, it is nuclear, because this is the nucleus is where this all comes from. So radioactivity is technically just the emission of subatomic particles or electromagnetic radiation by the nuclei of certain atoms. So here's our silly little cartoon of an atom. It's silly in the sense that we know that they don't really look like this, but it's a great model for what we're going to talk about today because it shows clearly the protons and neutrons that make up the nucleus. These are also called nucleons. And then the electrons surrounding the atom. And all radioactive atoms have an unstable nucleus, and that is going to spontaneously decompose to gain stability because remember, moving towards lower energy is pretty much what drives all processes on Earth. And this process will affect both electronic and nuclear structure, whereas when we talked about electronic changes and sharing electrons or ionizing, we were really talking about changes only to the electronic structure, whereas these changes will affect both. And we're going to start off by talking about only these types of radioactivity, alpha, beta, and gamma. There are other forms, but we're not going to discuss those in this course. So I want to review our isotopic notation before we get started. So we have our atom here, carbon, and we have our mass number and our atomic number. And the generic form here is X is our chemical symbol, Z is our atomic number, and A is our mass. A, the mass, is the sum of the number of protons and neutrons in the nucleus, whereas the atomic number Z is the number of protons. Remember that the identity of the atom is dictated by the atomic number. So it doesn't matter what the number up here is, you will know the identity of the atom by only looking at the atomic number, the number of protons. All carbon atoms have 6 protons. All carbon atoms do not have a mass of 12. There are also carbon-13 and carbon-14 atoms, which we'll talk about when we get to carbon dating. So if you want to know the number of neutrons that is in an atom, you have to subtract the atomic number from the mass number. And so we don't have the number of neutrons listed here. We can also do isotopic notation for subatomic particles. This is slightly different because instead of an atomic number, it's really charge. You can kind of think of it as the atomic number, the number of protons, but charge makes more sense when you're thinking about these subatomic particles. So the mass for both a proton and a neutron is 1, and the mass of an electron is 0. Now, technically, the mass of an electron isn't 0, but it is 0 compared to a proton or a neutron. Then you have your charge, 1 for proton, 0 for neutron, and -1 for electron. It's pretty similar to the atomic number because protons are positively charged, and an electron is the opposite charge of a proton, so you kind of have a -1 proton on an electron, and you don't have any protons on a neutron. But really just think of this as charge. So the first type of radiation I want to talk about is radioactive decay. And this happens when an unstable nucleus emits an alpha particle. And an alpha particle is the equivalent of a helium atom. Beta decay happens when an unstable nucleus emits a beta particle, which is the equivalent of an electron. So what this causes is it basically changes a neutron to a proton. And that will change both the electronic and nuclear identity of this atom. Whereas in alpha decay, you only change the nuclear identity. Positron emission is a special type of beta decay when an unstable nucleus emits an anti-electron, so basically a proton becomes a neutron. It's the opposite. It's not the reverse of this because it's not gaining an electron. It's actually kicking out a positron, which is just a positively charged electron. And so the proton becomes a neutron. And so again, this changes the identity of the compound. Finally, we have gamma ray emission. And it's not a particle, it's a ray, because what we're talking about is emitting a photon, emitting a discrete packet of energy. And so you see with your gamma ray, you have a 0 and a 0 here because there's no mass and no charge. It is a burst of high frequency, high energy electromagnetic radiation. It doesn't have a charge or a mass, and this usually occurs alongside other kinds of radiation, so usually alpha. So if you have an alpha decay, you pretty much are always also losing some gamma rays. So let's think about the consequences of radiation. What's happening? So just as a reminder of our electromagnetic radiation chart here, we have our radio and microwaves and infrared waves, and then we have our visible light here in the middle, followed by ultraviolet light, X-rays, and gamma rays. The further to the left you go on this chart, the shorter the wavelength, the higher the frequency, and the higher the energy. So remember, wavelength is the distance between 2 points on a wave. And frequency is how many times that wave passes a point. And so these have very short wavelengths, very high frequencies, very high energy. So gamma rays are the highest energy. They have the ability to pass through solid materials. So do X-rays. This is why when you go to the dentist, you have to wear that really heavy lead apron if they're going to take X-rays of your mouth, because we don't want to expose your organs to any more X-rays than we have to. X-rays and gamma rays have the ability to penetrate deeply, and they have very high energy, but they aren't very good at knocking electrons out of other atoms. They don't have enough mass. But when you have beta particles, they have middle of the road energy and penetrating power, and they also have middle ionizing energy. They can knock electrons out of other atoms sometimes. Alpha particles, they are really bad at penetrating, but they're the heaviest, and they create free radicals. So if you wanted to compare these, you could think of this as like a train or a semi-truck, tons of energy, but not very easy to penetrate. So they just kind of have to just go in its one direction. They don't really have an ability to like move around. Beta particles are like a car. When driving that on the freeway, you can kind of change lanes a little bit, whereas these gamma rays are like a motorcycle that can just drive in between a stopped line of cars at a traffic light or something like that. So these are our largest particles, best ionizing, least penetrating, whereas these are our highest energy, greatest penetrating, least ionizing. The other thing about alpha particles is these cannot penetrate your skin, so they're not really a hazard if it's just out in the world. But if you were to ingest this, then it can damage your organs because it has access to them. So your skin protects you from alpha particles as long as you don't ingest them. So much like we can with chemical equations, we can write nuclear equations and balance them. And so unlike with chemical equations, we don't necessarily retain the original identities of the compounds. But like chemical equations, we have to balance them by charge and mass. And so let's look at alpha decay. We have the atomic number decreasing by 4 and the mass number decreasing by 2. So you'll notice that since our mass number decreases by 4, that's backwards. The mass number decreases by 4 and the atomic number decreases by 2. I apologize for that typo. I will fix it on our slides. So we have, if we're going from 92 protons to 90 protons, we have effectively changed the identity of this atom. So let's write the nuclear equation for the alpha decay of polonium-216. So we know that 216, this number here is always the mass number. So you'll have your atom name or chemical symbol first, and then a little hyphen, and then you'll have the mass number. So you write this as polonium-216, and then you get this number here off the periodic table. So you will want to make sure that you have access to a periodic table when you are working with this type of material, because you'll have to look them up to get your number of protons. So it's polonium-216, it has 84 protons, and then it's going to decay to a new compound, a new element, and a helium atom. So what you do is you subtract 4 from 216 and 2 from 84 to fill in these numbers. And once you know those numbers, you can figure out the identity of your new atom. So when we do that, we see that we get lead, which has 212 as their mass number, and 82 is the atomic number. In beta decay, the atomic number increases by 1, but the mass number remains unchanged, because remember, electrons don't have mass. So no mass is going to be affected by this. However, if you get rid of an electron, you've essentially turned a neutron into a proton. And so if you want to write the nuclear equation for the beta decay of neptunium-239, we follow the same process we did before. And we go from an atomic number of 93 to an atomic number of 94, and the mass number remains unchanged. So we go from neptunium to plutonium. In this example over here, we go from carbon-14 to nitrogen-14. Our mass does not change, but the atomic number does. We go from 6 to 7. With gamma ray emission, this is typically occurring in conjunction with other radiation. You don't generally see it by itself, and it doesn't change the mass or the charge of the parent nuclide. So you could have your uranium-92 going to thorium or technetium-90, and then you would have, thorium-90, and your helium, and then you also have the gamma ray. So the change in charge and mass on this right here is solely from this. This doesn't add anything because there's zeros on it, which is what that tells you. There's no mass or charge. And so we have this reaction occurring, emitting an alpha particle, and then also some energy is emitted as well. So let's do a quick concept check here. We have this arrow labeled X, the red arrow here, and this blue arrow labeled Y, and we want to know which of these correspond to what kind of decay. So here we see that this is a number of protons, and this is increasing by 1, a number of neutrons increasing by 1. Okay, so since we're dealing with protons and neutrons, we know that we have to have some sort of alpha decay happening. And we see that all of these have alpha decay as options, so that's good. Okay, and we'll note that if we have X and it goes from 2 protons, it loses basically 2 protons. So 2 protons are kicked off. The way for that to happen would be helium, losing a helium atom, right? And so that means that X probably is showing our alpha decay. And we see that A and C give us both of those options, alpha decay. Okay, so what is this blue arrow showing? Is it showing us positron emission or beta decay? Well, if we're going from a neutron to a proton, that means that we are losing an electron, so that must mean beta decay. So the answer to this concept check question is C. X corresponds to alpha decay, and Y to beta decay. So what does exactly an unstable nucleus mean? Why would a nucleus ever be unstable? Well, there are two forces at play in a nucleus. There is the strong nuclear force, and there's the electrostatic repulsion or the Coulombic forces. The strong nuclear force is really what's holding our nucleus together. And I don't really fully understand it. I know that there are quantum mechanics that govern the behavior of nucleons the same way that quantum mechanics dictates the behavior of electrons, but I don't know a whole lot about that. It is not my area of expertise. But I do know that this strong force is what has to be overcome in order for a nucleus to break apart, and that there is a competition between the strong force and the Coulombic forces. These strong forces act over a shorter distance than the Coulombic forces, which means that these have to be very tightly packed to each other in order for them to overcome that repulsion, because only opposites attract, right? The same charges repel each other, so there's electrostatic repulsion, and at some point, too many neutrons is going to be a problem. And here we have quantum numbers for protons and neutrons, just like electrons. They're J, T, and P. These are different. You don't have to know any of these. I just want to show you that there are energy levels for neutrons and protons. And the thing is that once you get more and more and more neutrons, you're going up to higher and higher and higher energy levels. So there's a ton of energy held in this nucleus, and eventually you get to a tipping point where the strong force can't overcome. It's not enough to compete with the repulsive Coulombic forces and maintain that high energy level for the neutrons. So this is kind of what holds together a nucleus, and that is really the extent of my knowledge there. If you're really interested in this, there are some excellent videos on Crash Course in Chemistry on YouTube that I would recommend, but that is the extent of my knowledge there. So our radioactive elements, everything above bismuth is unstable. So these are all radioactive, and remember these are smaller numbers than polonium. There are some exceptions. We have technetium, and then we also have this one, 61. So the reason for that is that if you have an element that has an odd number of protons and an odd number of neutrons, those usually are very unstable. There's only 5 elements that have odd numbers of both nucleons that are stable, and I don't think either of these I think both of these have odd numbers of those. So that's why these are unstable, even though they're a little bit smaller. But then everything above bismuth is radioactive. So let's talk about why that is. So it's not just the force, we also look at the ratio. So it's not just the sheer number of neutrons or protons, but the ratio of neutrons to protons. And we call this the NZ ratio. If NZ is too high, there are too many neutrons. If NZ is too low, there's too many protons. So here we show, these are all of the elements that exist, all of the formations that exist, they're all in yellow. And this is an NZ ratio of 1. And you'll notice that down here, that green area, which is nicknamed the Valley of Stability, this green area matches that line, and then eventually it kind of breaks away from that line and curves up. And so everything that's green, stable, not going to emit, it's not going to spontaneously emit any particles, subatomic particles. Notice that above 83, we have nothing that's stable. These are all radioactive. And so let's think, if we have PB 192, so number of neutrons, 192 or 212. So we know that we're probably for 212, we're going to be up on this side. And then for 192 on this side. So I think that for one of these, we're going to have beta decay, and one of these, we're going to have positron emission. Okay, so we're going to have too many neutrons for lead-212 and too many protons for 192. And so you can kind of guess based on this picture if an element is going to be stable or not. So here you see that like rubidium 100 is stable. But if you had something like rubidium 102, then that is not going to be stable and there's going to be some emission there. And the last thing I want to talk about is the radioactive decay series. And so again, remember atoms with an atomic number greater than 83 have unstable nuclei. And so this is kind of what happens. Now you don't have to memorize this at all. It's not important, but I want you to notice that they decay via steps. That is what is critical here to understand. And you'll notice that this looks very familiar from our concept check earlier, our alpha decay and our beta decay. So here we have uranium-238. It is the heaviest naturally occurring element. All the elements beyond that that are heavier were made in a lab. And it has a half-life of 4.5 billion years. So it's just kind of here. It's not leaving. And what happens is it spontaneously decays. So this here is an alpha decay. So we go from 238 to 234. And then there is from this now has its own half-life of 24 days, loses a beta particle, and then 6.7 hours is the half-life for the next compound, and it loses a beta particle. Then we've got some alpha again, and you'll notice these are the half-lives. And then you have polonium-218. Now at this point, you have options. We can have polonium, it can decay via either beta or alpha. And you'll notice that if you do beta decay twice, you've now changed elements, but you've kept the mass the same. And so eventually there'll be points where either alpha or beta decay happens. I am not sure what dictates which one happens, but I do know that in these types of scenarios where you show like this, that they both are happening. So for this block of polonium-218, some of the atoms will emit beta particles and some will emit alpha particles. So in our next lecture, I'm going to do some problems with you, some example problems that show us how to work with these numbers that are in this radioactive decay series and use compounds and like uranium or carbon to calculate the age of rocks and other artifacts.